Okay, let's look at how this works using SPSS. So let's look at the process for running regression using SPSS. So I just have a screenshot of the 2012 AC data file. And so under Analyze, you're going to select Regression, and then you're going to select Linear. So there are all kinds of things. So if you look, there's log linear, there's generalized models, there's all kinds of extra things in here. We're going to focus just on our linear regression right now. So once we've selected it, we're going to end up with it's going to open up a regression box or a regression window. We're going to put our dependent variable here, and we're going to put our independent variables here. So we're going to run analysis of how a person's sex and how much school their father completed, so their father's highest year of education, impact education. Why might we do that? We may have reason to believe, to hypothesize, that gender affects educational attainment. And so we want to run an analysis to check on the effects of gender on educational attainment. And we also think we have reason to believe that how much education your father has is going to impact how much education you get. And we know that there is some existing data on this, that the further your parents go in school, the further you're likely to go in school. So if your parents went to college, you're likely to go to college too. If your parents did not go to college, you're less likely to go to college. You may end up with more education than your parent, but that's going to be a limiting factor. And that's what previous data tell us. So we want to look at how sex and father's highest education level impact your education level. If we can predict how much education you're going to have based on these two independent variables. So once we have selected our variables, there are a whole series of options here, some additional buttons that we can push. So I want to talk a little bit about where each of these takes us and why we might choose to click on some of the things that are within those boxes. So let's start with the Save box. So the Save box, when you click on that, it opens up this window here. And unstandardized will already be there. There's some additional measures down here. There's some influence statistics down here. You can do prediction intervals. You can create coefficients. You can do all kinds of additional things. What I want you to look at is the residuals. So you will automatically, I think, have the unstandardized residuals, but you can also do studentized or normalized residuals as well. And so the residuals, if you remember, are useful in identifying outliers, because that's the name or another word for prediction error. It's also disturbance term, which is the language that Allison uses later on. So this is a measure of those distances between observed and predicted values. So if some of those distances are really quite large, that gives us a sense that there might be outliers that are having an effect, right? And so that might be important. So we can get a report on these residuals, and the normalization, that studentized version, will give us a sense of whether there are outliers. Under the Statistics button, we have a statistics window that pops up. Estimates and model fit will already be there. You can also have it do confidence intervals for you. So it will run confidence intervals, and it will show you the upper and lower limits of those confidence intervals. And we talked about how to interpret those previously when we did that earlier in the semester. You can also, in this same area, select collinearity diagnostics. And these will help you to determine how much correlation there is among your independent variables. So we talked about this last week, and what you get is a series of tolerance statistics that gives you a measure by taking all the bivariate correlations of the independent variables together. We don't really have any reason to believe that your father's level of education is associated with your gender, right? I mean, men and women have fathers, and there's no reason to believe that women's fathers have more education than men's fathers. Doesn't make any sense. So we don't expect there to be anything. But if you are concerned that some of your independent variables may be correlated, maybe collinear, then these collinearity diagnostics will provide you with a measure of how serious that could be, how much of a problem that might be in your model. And then next week, we'll talk about some of the ways that we deal with that, because Allison has an entire chapter on multicollinearity. Under plots, we can, this also helps us with regard to looking at collinearity. We can plot the residuals. And so this is the residual for, this is the predicted residual, and this is the calculated residual. So these are the predicted values. So predicted values and the residual, standardized residuals. So we put these in so that the residuals the standardized residuals go under Y, and the predicted residuals go under X, and we have it run. We can click on a histogram, and it will give us a way to visualize the data and identify outliers. So that residual model, it will normalize that, and we will kind of check that. So we can use these plot functions to check also for homoscedasticity, which give us a sense of whether we have any, and we'll talk a little bit later about that, if we have any problems with the way that the data is distributed across the regression line. So when we run, and I've run the things that I've illustrated there, we have our first model summary. That's our first table that we get in our output. And our R-square is 214, so 0.214. So this tells us that 21.4% of the variance in the highest year of school completed is explained by father's education and sex. So that's really all we need from that first table. That's all we need to worry about from that first table. From our ANOVA table, we can see that we have a significant F value, which tells us that at least one of our independent variables is not 0, right? Because that's testing it against that null hypothesis. So it's our predictive value of at least one of the independent variables is not 0. And then we can see our degrees of freedom is 2 because we have 2 independent variables, highest year of school completed for the father and the respondent's sex. Our third table is our coefficient table. And so we have our residuals. Here's our constant. We have our residual values. We have our standard errors reported. We have the standardized coefficients. And again, looking at those standard coefficients gives you a sense that education is a far better predictor than sex is, because the value is so much different between those two. But we also get that sense here. Sex is not significant, but father's education is. So this is 0.09. We want it to be less than 0.05. So sex is not a statistically significant predictor of year of school completed. Our equation for this line, and again, I think it's a good idea to practice writing out the equation because it gets you in the habit of pulling those numbers from the table and knowing where they go. So we have the predicted value of Y, which is highest year of school completed. That's our dependent variable, 9.766, which is our constant, plus 2.241 for males, or X sub male for that particular variable, plus 0.328 pause education. So remember, this is a dummy variable. So interpreting this variable, we would be saying that males, okay, that there is 0.241 additional years of education for males than females, right? So that's how we would interpret this coefficient. So assessing multicollinearity, these tolerance statistics here, this piece of the table, the value 1.001 indicates that there is no major issue with multicollinearity. And I found a kind of guideline from Scopel that on how to interpret the VIF values. So if all the values of VIF are near 1, that indicates no collinearity between the predicted variables. We're pretty close to 1. And then less than, a little bit more than 1 to 5 indicates moderate collinearity, and then greater than 5 indicates serious collinearity. And if you have values that are greater than 5, there are probably some additional things you need to do to address those issues, to address that collinearity. This is actually not to check for that, it's to check for heteroscedasticity. I apologize for the error in the slide, but our scatter plot doesn't show any, this is the regression of the standardized predicted value and the standardized residual, and we're not seeing anything that would make us think that there's no patterning in the distribution of scores. And so we have every reason to think that heteroscedasticity is not a problem in our output or in our analysis. And then our histogram helps us to check for normality. So our residuals are relatively normally distributed. There's no coning of the data. So our assumptions are pretty much in check.